Well, we have already discussed about the Virial Theorem, you remember, and we discussed this as a consequence of the equation of hydrostatic equilibrium, and we obtained it when we applied this equation to an ideal gas. And another interesting application was finding the mean temperature for the ideal gas using this hydrostatic equilibrium equation. Anyway, what today I would like to discuss with you is a little bit more on your Virial theorem, but from a different viewpoint. Now, the first thing is that you see, when did we first encounter? When did you first encounter Virial theorem? You remember? I think it was in class 11, gravitation, right? What you did observe was that for a two-body bound system, for a bound two-body system, we have seen that the angular momentum and the gravitational potential, angular momentum and gravitational potential, they basically combined and to produce a unique orbit. This is important. You must remember this. The satellite orbit. Yes, and for which the velocity is known at each moment. So basically, this is what we did. We talked about the unique orbit, but basically we used this Virial theorem. But you didn't knew this name at that time, but basically it was the result that you observed, the relation between the kinetic energy and the gravitational energy. It was just the statement of Virial theorem. Now, what we are going to do is basically we are going to combine these two apparent diverse subjects of gravitation and thermodynamics into a single subject. Let me talk about it. Basically, you see, the Virial theorem provides a powerful global constraint on the, it basically provides a global constraint on the stability of a gravitationally bound system, and this is central to many astrophysical problems. Now, talking about the origin, where did it originate, this important theorem? Well, you see, this Virial theorem originated in mechanics. The prime example is the motion of ensembles of point masses moving under the influence of their collective gravitational field. Now, we treat the force, so basically we are talking about motion of ensembles of point masses moving under the influence of their collective gravitational field. Okay, now what we do is that we treat the force as the result of the entire collection of masses, but remember, each particle moving independently and without collisions. So let's assume that we have a set of particles that are bound within a background potential. Now the particles are assumed to be collisionless and the motion is solved for each particle individually. Otherwise, we place no constraints on the energies of the bodies. Now, the equations of motion can be written in component form, right? So we can write m d2 xi divided by dt2 is equal to fi, where for simplicity we are assuming that the particles have the same mass. Now if we take the scalar product with the displacement xi minus xi0 and look for a scalar quantity that is analogous to work, then what we will obtain is this: m xi minus xi0 I double dot is equal to half m d2 square dt2 minus m xi dot square. This is equal to w. Now notice that the first term is the second time derivative of the moment of inertia here, which measures the rate of distortion of the body, and the second term is basically mv square, is twice the kinetic energy, and the last term is the net potential energy, this one. Now if for the moment we restrict our attention to the steady state in which the symmetry of the body and the global mass distribution is unaltered, steady state, symmetry of body and global mass distribution is unaltered, then what will happen? The moment of inertia term will be 0 and we will get this familiar equation, which is the Virial theorem, and this was first derived by Clausius. Okay, in the mid 19th century. So basically what this says in effect is that there is a limit to the amount of work. So this means that there is a limit to the amount of work that can be obtained from a bound system. This is very important. To be more specific, let's now restrict our attention to a gravitational field. Now in this case, the total mass is simply the volume integral of the density, and for simplicity we will assume that the spatial density is constant. Okay, then you see the gravitational potential energy is just minus 3g m square by 5r. R is the radius, m is the mass, and this is just minus twice of k. Right. Now m is the total mass and r is the mean radius of the distribution of masses, and the kinetic energy k is just half m v average square. This is capital M, of course, and v average is the mean velocity. Okay, now you see this provides a constraint on the kinetic energy. So this relation now provides a constraint on the kinetic energy of the system given a potential energy, but it also indicates that the motion is restricted to bound states. So now our Virial theorem provides a constraint on kinetic energy of system given a potential energy. Also, it indicates that the motion is restricted, to bound states for which, you see, the total energy E is equal to k plus omega, or basically for which E is equal to half of omega, which is basically the gravitational bounding energy of the system. Now it is important to note that we have made no use of the random motions. So in this case, the assumption is that the individual particles move within the gravitational potential of the system and that they are dispersionless. That means each orbit is individually subject to the same global constraint. So you see, we have talked about how this provides a limit, or basically it tells you about the unique orbit scenario, the same thing, the bound system, which orbits will be there. So it is telling us basically that there is a constraint on the kinetic energy for a given potential energy, and also indicating that the motion is restricted to this particular bound states which satisfy them. Okay, now let us go forward and do a merger of mechanics plus thermodynamics again, which I was talking initially. For that, let us take the equation of state to be polytropic when deriving the equilibrium structure of a simple gas acting only under its own gravitational field. Now we can write the kinetic energy of this gas in terms of temperature as dk is equal to 3 by 2 kBT dN, or just 3 by 2 R by mu T dm, where this N is the total number of particles in the mass. Now the internal energy is du Cv T dt dm. Now the connection between the two, that means mechanics and thermodynamics, comes from the relation between the specific heats, which is basically Cv into gamma minus 1 is equal to R by mu. Now on substituting this, we get this relation. K is equal to 3 by 2 gamma minus 1 into U. Now what about the total energy of the body? We know the total energy is U. You see, E is equal to U plus omega. And also we know that omega is equal to minus twice of K. So as a result, we can write the total energy as 4 minus 3 gamma into U, or we can write this as 4 minus 3 gamma divided by thrice of gamma minus 1 to omega. Now we see that E tends to 0, as so implications is gamma tends to 4 by 3. In other words, the system becomes unbound if the equation of state is too soft. Okay, and it is important to note that we have not made any assumptions about the geometry of the body. Now you see, a simple consequence of the Virial theorem is that a self-gravitating gas bag that is losing energy, so a self-gravitating gas bag which is losing energy must contract if its density is constant through the interior. Now the rate of energy loss, it is basically E dot equal to L. L is the luminosity, so that we can write R by R dot is equal to 3 by 10 into G m square by RL. I am using the gravitational energy expression, and this is the Kelvin-Helmholtz time. Kelvin-Helmholtz time, contraction time. Okay. Now this time scale is very wrong for the age of the sun. If I write it in solar units, then I will have to write something like this: 2 into 10 to the power 7 years m by m solar whole square r by r solar to the power -1 and L by L solar again to the power -1. Now if I talk about the solar values, then it is just 2 into 10 to the power 7 years. Of course, we know that the age of the earth is even more. So this means the time scale is very wrong for the age of the sun. But it is a fair estimate of the contraction of a star before the onset of nuclear reactions. So this is a fair estimate of contraction time scale of star before the onset of nuclear reactions, when only the heat from the initial collapse is being radiated away. Now we can also use this very simple result to estimate how long it takes for an optically thick layer to cool. You see, if the layer has a mass, delta m, then the thermal time scale is how much? Analogously, you see, the thermal time scale is basically T thermal is equal to G m delta m by R into L. Okay. Now, let me talk about a very interesting concept. Of course, I have talked about this previously, but let me again spend some more time on it. And the concept is known as Gravitothermal Catastrophe. What is it? Now you see, since the Virial Theorem relates the internal velocity dispersion to the total energy, we can easily see that this is the case. Kinetic energy, total energy. Now, this is a very simple relation, but it has a very profound consequence for the evolution of the self-gravitating system, regardless of the number of bodies involved. How? How can you say this is important? You must be wondering. Now you see that what this equation means, that the specific heat is negative for a gravitationally wound system. Now in consequence, if the system cools, it becomes more tightly bound. That means its total energy becomes more negative. So basically, if system cools, then it becomes more tightly bound, right? And the total energy becomes more negative. Now this means that the velocity dispersion increases, right? So the final state of the system is a collapsed core. So final state is a collapsed core in which the density increases without bound. Density increases without bound, without any limits. Now one way of saying is that you can also say that a self-gravitating system can never lose energy rapidly enough, okay, to cool. This is very important. Okay, so we have discussed a lot of things, and this is basically your gravitothermal collapse. Fine. Okay, so you see, let me again say some more. Basically, we have talked about the various consequences of the Virial theorem, and we do know that a self gravitating body obeys the Virial theorem. So as it cools, it contracts, and the cooling can occur by photon or neutrino emission, or by conduction as well. And if this energy loss is sufficient enough to maintain isothermal condition, then the medium becomes progressively denser. This is what I am saying. And remember, as it becomes progressively denser, it can cross the degeneracy limit as well. Otherwise, if the degeneracy sets in, the temperature will not decrease, because you remember the pressure expression for a degenerate electron gas, there the temperature was absent. So this means that in a degenerate gas, the pressure increases, density increases, but temperature remains same. Okay, fine. Okay, before I finish today's lecture, let me spend some more time on this particular expression over here. You see, I've just talked about this relation, but basically what I have told you is that this E must be less than 0. It must be negative for a bound system, right? So what does this mean from this expression? This means that 4 minus 3 gamma, it must be less than 0, or that means gamma must be greater than 4 by 3, and this is the condition for stability. Okay. Now, what will happen if gamma is less than 4 by 3? Then you see E is greater than 0, and it means we have got an unstable system. Now, for non-relativistic particles, gamma is equal to 5 by 3, right? And so it's okay. We have got a stable system which is more than 4 by 3. Okay. Okay. Fine. So now finally, regarding your Virial theorem. Good. So we have discussed a lot of topics, and let me just recapitulate a few of them. So if I ask you, what are the various applications of Virial theorem which comes to your mind, what will you say? Now the first thing is that it naturally arises, this Virial theorem, in the case of orbital motion of a planet around the sun. You see, let small m, capital M and small m be the mass of sun and your planet respectively. Then for a circular orbit of radius r, circular orbit radius r, if the planet moves with the velocity v, then the gravitational attraction on the planet is balanced by the centrifugal force due to orbital motion. That means mv square by r is equal to gmm by r, and this is basically twice half mv square minus gmm by r is equal to 0, or twice of E kinetic or E thermal plus E gravitation equal to 0. So basically Virial theorem, this I was talking about. Remember, unique orbit using Virial theorem. Okay. The next thing which comes to our mind, application, is that the Virial theorem can be used to estimate the average temperature of stellar interior, and that temperature is known as virial temperature. Okay, now you see, it can also be used to estimate critical pressure required for star formation. In the case of an isothermal gas sphere, this I will talk about later on during star formation class. And so basically we can use the Virial theorem to estimate the necessary conditions for protostellar collapse. Also, very interestingly, you see, we can use the Virial theorem to discuss the stability of neutron stars. Fine. Again, this I will talk about when I speak about in the relativistic astrophysics section. So it's a very important tool, very good. So what are the limitations of Virial theorem? Right. Now you see, the first is that this Virial theorem applies only to point particles. Now if bodies have shape and size, then some of the energy changes that take place when they interact goes into spin or some distortion. Also, you see, the Virial theorem don't apply to particles that are not in bounded system. Example, particles in an explosion. Two very basic cases I have talked about.